A powerful combination of catalysts effectively transforms carbon dioxide into solid carbon nanofibers. Greetings and salutations to everyone. Our video today focuses on an intriguing development by scientists at the US Department of Energy's Brookhaven National Laboratory and Columbia University. They have successfully devised a method to transform carbon dioxide into carbon nanofibers, providing a valuable reinforcement for cement. This groundbreaking process involves a combination of electrochemical and thermochemical reactions operating at low temperatures and ambient pressure. Additionally, the process generates hydrogen gas, which presents an exciting alternative fuel source. The researchers are optimistic that this innovative approach could potentially counterbalance or even result in negative carbon emissions. And now, without any further delay, let us begin our in-depth exploration of this fascinating topic. According to Jingguang Chen, a professor of chemical engineering at Columbia University and the leader of the study, carbon nanofibers have the ability to reinforce cement, effectively trapping carbon within the concrete for a minimum of 50 years, if not longer. This presents an opportunity for the world to transition to renewable energy sources that do not produce carbon emissions within that time frame. In addition, the process also generates hydrogen gas, H2, a highly promising eco-friendly fuel source that, upon utilization, generates absolutely no emissions. The concept of capturing or transforming CO2 into different substances as a means to address climate change is not a novel one. However, the mere storage of CO2 gas can potentially result in leaks. Furthermore, numerous CO2 conversions yield carbon-based chemicals or fuels that are immediately utilized, subsequently reintroducing CO2 back into the atmosphere. According to Chen, what sets this work apart is our attempt to transform CO2 into a solid, practical form that adds value. Materials composed of carbon, such as carbon nanotubes and nanofibers, possess a multitude of desirable characteristics, such as exceptional strength and efficient thermal and electrical conductivity. However, the process of extracting carbon from carbon dioxide and facilitating its assembly into these intricate structures is far from straightforward. One approach involves subjecting the carbon dioxide to intense heat, with temperatures surpassing 1,000 degrees Celsius. According to Chen, the idea of mitigating CO2 on a large scale is highly impractical. However, a more feasible and attainable temperature of around 400 degrees Celsius has been discovered for a process to take place. The key to this breakthrough was dividing the reaction into stages and utilizing two distinct catalysts, substances that facilitate the merging and reaction of molecules. Lead author on the paper, Zhenhua Xi, explained that by breaking down the reaction into multiple sub-reaction steps, it becomes possible to utilize various energy sources and catalysts for each individual part of the reaction. Initially, the scientists made the observation that carbon monoxide, CO, serves as a superior precursor compared to carbon dioxide, CO2, when producing carbon nanofibers, CNF. Subsequently, they retraced their steps to determine the optimal method for converting CO2 into CO. Their previous research led them to opt for a readily accessible electrocatalyst composed of palladium on carbon. Electrocatalysts facilitate chemical reactions through the use of an electrical current. By introducing electrons and protons, this catalyst effectively separates both CO2 and water, H2O, into CO and H2. In the next phase of their research, the scientists utilized a thermocatalyst composed of an iron-cobalt alloy that is activated by heat. This particular catalyst functions effectively at temperatures of approximately 400 degrees Celsius, which is considerably less extreme compared to the conditions necessary for a direct conversion of CO2 to CNF. Additionally, the scientists made an interesting finding. The inclusion of a small amount of metallic cobalt significantly boosts the production of carbon nanofibers. We are utilizing a combination of electrocatalysis and thermocatalysis in this tandem process to achieve feats that would be impossible with either process alone, stated Chen. In order to uncover the intricacies of these catalysts' operations, the researchers conducted an extensive array of experiments. These encompassed computational modeling studies as well as physical and chemical characterization studies at Brookhaven Labs' National Synchrotron Light Source 2, NSLS-2, utilizing the quick X-ray absorption and scattering QAS and inner shell spectroscopy ISS beamlines. Additionally, microscopic imaging was performed at the electron microscopy facility located at the Lab Center for Functional Nanomaterials, CFN. To analyze the interactions between the catalysts and the active chemical environment, the scientists employed density functional theory, DFT, calculations, which allowed them to examine the atomic arrangements and other properties of the catalysts. The examination of catalyst structures under reaction conditions is the focus of our research, as we strive to identify the stable phases. Leading the charge in these calculations is study co-author Ping Liu from Brookhaven's Chemistry Division, who elaborated on our approach. Our analysis delves into the interaction between active sites and reaction intermediates, shedding light on the bonding process. By pinpointing the transition states or barriers between each step, we gain invaluable insights into the inner workings of the catalyst during the reaction. The transformations that occur in the catalysts during the reactions were monitored through X-ray diffraction and X-ray absorption experiments conducted at NSLS-2. These experiments utilized synchrotron X-rays to uncover the process by which metallic palladium in the catalyst is converted into palladium hydride, a crucial metal in the production of H2 and CO during the initial stage of the reaction. In the subsequent phase, Z expressed the desire to explore the composition and arrangement of the iron-cobalt system during the reaction process, as well as identify methods to enhance the iron-cobalt catalyst. Through X-ray experiments, it was verified that a combination of iron and cobalt alloys, along with an additional amount of metallic cobalt, were essential for the conversion of CO into carbon nanofibers. Liu, who utilized his DFT calculations to shed light on the process, stated that the two entities collaborate in a sequential manner. The alloy's cobalt-iron sites play a crucial role in the breakdown of carbon monoxide CO bonds, as indicated by our research. This process generates atomic carbon, which serves as the foundation for constructing carbon nanofibers. Additionally, the surplus cobalt aids in the formation of CC bonds that connect the carbon atoms. The examination of carbon nanofibers with and without catalysts involved a comprehensive analysis using transmission electron microscopy, TEM, at CFN. CFN scientist and co-author of the study, Soyeon Hwang, commented on the TEM analysis, highlighting its ability to reveal the morphologies, crystal structures, and elemental distributions within the carbon nanofibers. According to Chen, the visuals indicate that during the growth of carbon nanofibers, the catalyst is displaced and moved away from the surface. This displacement facilitates the efficient retrieval of the catalytic metal for recycling purposes. According to him, acid is employed to extract the metal while preserving the carbon nanofiber, allowing for the concentration and subsequent recycling of the metals as a catalyst once more. According to the researchers, the favorable evaluation of the energy and other costs linked to the process is influenced by the ease of catalyst recycling, the commercial accessibility of the catalysts, and the relatively gentle reaction conditions required for the second reaction. Chen emphasized the significance of both the analysis of the CO2 footprint and the recyclability of the catalyst in practical applications. The technical findings, along with these additional assessments, demonstrate that this dual approach provides a pathway to convert CO2 into valuable solid carbon products and generate renewable H2, contributing to the decarbonization process. Should these processes be powered by renewable energy sources, the outcomes would be genuinely carbon negative, thereby creating novel prospects for mitigating CO2 emissions. The DOE Office of Science, BS, provided funding for this research. Computational resources at both CFN and NERSC, which are DOE Office of Science user facilities, were utilized for the DFT calculations. CFN and NERSC are located at DOE's Lawrence Berkeley National Laboratory. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.